Hi everybody, we're in section 1.4 of the trigonometry book, and in this section we'll be looking at reciprocal identities, signs and ranges of function values, Pythagorean identities, and quotient identities. And an identity is just an equation that's true for all angles. So we'll be using these kind of like formulas in a way. First, let's look at the reciprocal identities. We have seen these before actually. We've talked about how sine and cosecant are reciprocals, cosine and secant are reciprocals, tangent and cotangent are reciprocals, and these identities just kind of write that down in formula form. So this one says sine of theta equals 1 over cosecant of theta, or in words it says that the sine of theta is equal to the reciprocal of cosecant. And that means also that cosecant is equal to the reciprocal of sine. Then we have cosine is equal to the reciprocal of secant, and secant is equal to the reciprocal of cosine. Tangent is equal to the reciprocal of cotangent, and cotangent is equal to the reciprocal of tangent. And that leads us to example 1a. Find the cosine of theta, given that secant of theta equals 5/3. Now, the cosine is the reciprocal of secant, and so that suggests to us what we should do. I can turn secant into cosine by doing a reciprocal, but because this is an equation, I'll have to do the reciprocal of both sides. So if I do the reciprocal of secant, I'll get 1 over secant, and if I do the reciprocal of 5/3, I'll get 3 over 5. Now my reciprocal identity tells me that 1 over secant is equal to cosine, so cosine of theta is 3 over 5. Now for part B, find sine of theta, given that cosecant theta equals negative square root of 12 over 2. I know that we could do the same thing we did in part A. We could just start by taking the reciprocal of both sides, but I noticed that square root of 12 is a radical that can be reduced. So if we think of square root of 12 as square root of 4 times 3, then the square root of the 4 is 2, and that will leave us 2 outside the radical. These 2's will reduce, and we will have cosecant of theta equals negative square root of 3. Now let's do the reciprocal of both sides. The reciprocal of cosecant would be 1 over cosecant, and the reciprocal of negative square root of 3 would be negative 1 over square root of 3. Then our reciprocal identity tells us that 1 over cosecant is equal to sine, and of course with a radical in the denominator this must be rationalized, so I multiply top and bottom by the square root of 3, and that gives us negative square root of 3 over 3. Now this chart tells us the signs of the function values in each quadrant. And if you think about it, think about the definitions of the trig functions. Sine is y over r, cosine is x over r, tangent is y over x. In quadrant 1, x and y are both positive, so y over r is positive, x over r is positive, y over x is positive, and of course all of the reciprocals are positive. In quadrant 2, y is positive but x is negative, so y over r is positive, but x over r would be negative, and y over x would be negative. And that would mean if tangent is negative, so is cotangent, because they're reciprocals. If cosine is negative, so is secant, because they are reciprocals. If sine is positive, so is cosecant, because they are reciprocals. So in the second quadrant, sine and its reciprocal are positive. In the third quadrant, we have negative x and negative y. So y over r is negative, x over r is negative, but y over x is negative over negative, which is positive. So if tangent is positive, then cotangent is positive. If cosine is negative, so is secant. If sine is negative, so is cosecant. And in the fourth quadrant, we have positive x but negative y. That means y over r is negative, x over r is positive, y over x is negative, and then the reciprocals, you can see how they follow the same pattern. Now, if you look at it, in quadrant 1, all the functions are positive. In quadrant 2, only sine and its reciprocal are positive. In quadrant 3, only tangent and its reciprocal. In quadrant 4, only cosine and its reciprocal. Okay, here that is kind of summarized. All functions positive in quadrant 1, sine and its reciprocal in quadrant 2, tangent and its reciprocal in quadrant 3, cosine and its reciprocal in quadrant 4. And we can abbreviate this chart with this one. All functions in quadrant 1, sine and its reciprocal in quadrant 2, tangent and its reciprocal in quadrant 3, cosine and its reciprocal in quadrant 4. ASTC. And if you want to memorize the little mnemonic device, most people memorize. All students take calculus. Just start in quadrant 1 and go around counterclockwise. ASTC. And that will help you remember what functions are positive in what quadrants. And that's a really big help. Now for example 2, determine the sines of the trig functions of an angle in standard position with the given measure. So we want to determine the sines of the trig functions of an angle 87 degrees. Well, 87 degrees would be in quadrant 1. And I've drawn my little ASTC here. In quadrant 1, it says all the functions are positive. So that would be the answer to the question. And then for part B, the angle is 300 degrees, so let's draw 300. We know that at the negative y-axis we have 270, so 300 would be in quadrant 4. In quadrant 4, only cosine and its reciprocal are positive. So cosine and secant are positive, all the other functions are negative. And still on example 2, part C, negative 200 degrees. Now, because this is negative, we need to go clockwise. And so the negative x-axis puts us at negative 180. We need 20 more degrees. So negative 200 is in the second quadrant. In the second quadrant, only sine and its reciprocal are positive. That would be sine and cosecant, and all the other functions are negative. Okay, example 3. Let's identify the quadrant or possible quadrants of any angle theta that satisfies the given conditions. For part A, we're looking for the quadrant or quadrants where sine of theta is positive but tangent of theta is negative. Now if you draw your little ASTC diagram, the quadrants where sine could be positive are quadrant 1 and quadrant 2. But the quadrants where tangent is negative are quadrant 2 and quadrant 4, because tangent is positive in 1 and 3. So tangent is negative in 2 and 4. Now the only quadrant that these two have in common would be quadrant 2. So the only place that we can have positive sine and negative tangent is in quadrant 2. Now if you look at part B, we want to find the quadrant or quadrants where cosine is negative and secant is negative. Now if you think about it, these two are really giving us the same piece of information because cosine and secant are reciprocals. If cosine is negative, then secant is also negative by definition. So where is cosine negative? Well, if you look, cosine is negative in quadrant 2 and quadrant 3. But then so is secant because they're reciprocal functions. So cosine is negative and secant is negative in quadrant 2 and in quadrant 3. Now we're going to look at the ranges of the trig functions, and we're going to look first at the definitions that we've already memorized for these 6 trig functions. And here are sine, cosine, tangent, and the 3 reciprocal functions. So you remember y over r, x over r, and y over x. And so the first trig function that we're going to look at is sine and also cosine, because they behave very similarly. Now let's look at these 2 definitions. Sine is y over r and cosine is x over r. Now you remember that r is the hypotenuse of a right triangle, r is the vertical side, x is the horizontal side, and hypotenuse is always the largest side. So that means that y over r is always a proper fraction. Y is smaller than r. Or at the very most, remember when we had quadrantal angles, y could be equal to r, or x could be equal to r, but we know for sure that y and x can never be bigger than r. So that means that the value of sine and the value of cosine is always something less than 1. It can be positive or negative, but it's always stuck between -1 and +1. In a set builder notation, we could write that like this. Now they're going to use the letter y to stand for the function value. I don't want you to get that confused with this y, which was the vertical side of our right triangle, but this is a function value. So if you have, say, y equals sine of theta or y equals cosine of theta, then our function value can be anything as long as the absolute value of that function value is less than or equal to 1. In interval notation, we would say that sine and cosine values both have to be between -1 and +1. And they can include -1 and +1. So you remember interval notation from algebra, I hope. Now let's look at tangent and cotangent, and we have them here. Now we knew on the right triangle, we knew that r had to be the biggest side, but there's no rule about how y and x have to be. So y can be bigger than x can be bigger than y. It can be, the ratio can be anything that we want. And so there's absolutely no limitation on the size of y over x or the size of x over y. And that means that our function values for tangent and cotangent can be anything as long as they're real numbers, no imaginary numbers. And in interval notation, we would say anything from -infinity to +infinity. So all the numbers. Now secant and cosecant, if you look here at these definitions, now r is on top. X and y are on the bottom. X and y can be equal to r, but they can never be bigger than r. So that means that cosecant and secant both have to be, if we're talking about positives, they have to be 1 or more, because the number on top is bigger. If you're talking about negatives, they have to be -1 or less, like -2, -3, -4. So in range, and I keep saying range, in set builder notation, we would say that our function value can be anything as long as its absolute value is greater than or equal to 1. In interval notation, we would say all the numbers from -infinity to -1 and all the numbers from 1 to infinity are valid for secant and cosecant. Now look what's left out. The numbers between -1 and +1 are not included here because -1 to +1 is for sine and cosine. Less than -1 or more than +1 are for secant and cosecant. In example 4, we're going to look at each statement and decide whether it is possible or impossible. So question, is it possible for sine of theta to equal 2.5? Is there an angle whose sine equals 2.5? Well, we remember from the previous slide that the sine of an angle has to be between -1 and +1. So 2.5 is not between -1 and +1. Therefore, that is impossible. On part B, tangent of theta equals 110.47. We remember from the previous slide that tangent and cotangent can be any value at all from negative infinity to positive infinity. So yes, it is entirely possible for tangent to equal 110.47. Secant of theta equals 0.6. We have to think, secant is the reciprocal of cosine, and for secant and cosecant, the only valid values are less than -1 or more than +1. This is between -1 and +1. Therefore, secant cannot be equal to 0.6. That is impossible. For example 5, suppose that angle theta is in quadrant 2 and the sine of theta is 2/3. Find the values of the other 5 trig functions. Now, I've drawn the angle and it's in quadrant 2. It really doesn't matter how big it is. It only matters that it's in quadrant 2 because that's all they told us. Now we're going to use sine of theta equals 2/3. We're going to use the definition of sine as y over r to label our y side and our r side of our triangle. So y is 2 and r is 3. And now I'm going to use the Pythagorean theorem to find the missing side. We're looking for a leg, so we need to subtract the squares here. So x squared equals 3 squared minus 2 squared. X squared equals 9 minus 4, which is 5. That means x is square root of 5. Okay, now it's easy once I have the third side labeled. It's easy to find the 6 trig functions, and I have to keep in mind ASTC here. So we already know from the problem that sine is y over r. Cosine now is x over r, but it's in the second quadrant where sine is positive, cosine is negative. So negative x over r. Tangent is y over x, and it's in the second quadrant where tangent is negative, so it's going to be negative 2 over square root of 5. But now with that square root of 5 in the denominator, that will have to be rationalized. So we'll have negative 2 square root of 5 over 5. Now the other 3 functions I'm going to get from reciprocal relationships. So cosecant is the reciprocal of sine. Cosecant will be 3 over 2. Cosine is the reciprocal of secant. So secant is negative 3 over square root of 5. But that has to be rationalized. So it will be negative 3 square root of 5 over 5. Cotangent is the reciprocal of tangent. So I'll have to turn tangent upside down, but now here's a tip. Whenever you have a choice between a rationalized and an unrationalized value to do a reciprocal, always turn over the unrationalized one, because think about it. If I turn this one over, where is the radical going to be? In the bottom, where it will have to be rationalized. But if I turn this one over, where is the radical going to be? In the top, and I won't have to do any rationalizing. So cotangent of theta equals negative square root of 5 over 2. Now let's take a look at the quotient identities. Sine over cosine equals tangent, and the reciprocal of sine over cosine equals the reciprocal of tangent. So cosine over sine equals cotangent. You do not have to memorize these identities in this chapter. We'll definitely see these again in chapter 5, and we'll memorize them later. But right now I just want you to get used to the idea of dealing with these identities or these formulas, and just kind of understand that they're out there. And we're going to take a look now at why this is true. So here is a regular old coordinate system with an angle drawn on it, and I'm going to label the terminal side of this angle as r because it's the radius of our circle. And I'm going to point out that this point here could be anything, so let's label it x comma y. And let's remember that our definitions of the trig functions we already know. Tangent is y over x, sine is y over r, and cosine is x over r. And now let's take our tangent equals y over x, and I want to multiply y over x by 1, but I want to do it in such a way that it changes the look of the fraction. I'm going to multiply by 1 over r over 1 over r. Now if you think about it, this is a number over itself, so it's really just a big fancy 1, but it's going to change the look of the fraction. Y times 1 over r is y over r, and x times 1 over r is x over r. Now you'll recognize the top of our fraction, y over r, is sine, and the bottom, x over r, is cosine, and now you can see that tangent equals sine over cosine. And we could do the same thing for cotangent. Take the cotangent definition, multiply it by 1 over r over 1 over r. That gives you x over r over y over r. That gives you cosine over sine, which is cotangent. So that's how these identities came about. Now you don't have to be able to do that on your own, but I just wanted you to follow through and see why we have this identity or this formula that tangent of theta is equal to sine over cosine and cotangent is cosine over sine. Now the Pythagorean identities are sine squared plus cosine squared equals 1, tangent squared plus 1 equals secant squared, and 1 plus cotangent squared equals cosecant squared. I do not want you to be worried right now about memorizing these because we are going to see them again in Chapter 5. All of the identities we're learning here will come back again in Chapter 5. So we're definitely going to get another look at these guys. But I do want to start kind of getting your feet wet and getting you used to the idea that sine squared plus cosine squared equals 1. And these I would kind of call first cousins. They're just different forms of the same identity. Let me show you where these three guys came from. We'll start by looking at just a regular old coordinate system with an angle theta, terminal side here, or it could be anywhere, it happens to be drawn in quadrant 1, and we will label that radius of that circle as r, and this point here on the circle we'll call x comma y. Now I'm going to drop a perpendicular, just a little imaginary line straight down to the axis, and that forms for us a right triangle. And the horizontal side of that triangle would be x, because we know that from the point, and the vertical side would be y. Now by the Pythagorean theorem, I can write x squared plus y squared equals r squared. And then I can divide through by r squared. I can divide both sides of the equation by r squared. That's just algebra. And then notice that x over r would be cosine. So x squared over r squared would be x over r all squared. Same thing for y over r. And same thing for r over r. Now x over r happens to be cosine. So this is cosine squared plus sine squared equals 1 squared, which is just 1. Now this is not the usual way that we would normally write a cosine of an angle squared. Normally, instead of using the parentheses, we take the square and we put it in between the function and the angle. We do that because if you just didn't use the parentheses, it would look like the angle's being squared, but that's never the case. So to avoid confusion, we put the square here so that we can avoid using parentheses. And so this means the same thing as that. This is the function value squared. This is also the function value squared. I just wanted you to know what this notation means. So cosine squared plus sine squared equals 1. Now, We don't normally see the terms in this order. It's customary for sine to come first, so we just rearrange the terms. But there's our first identity. Now we are going to take that same identity and let's divide both sides of our identity by sine squared theta. So if I go through and divide everything by sine squared, it looks like this. Now, sine over sine would be 1, so that's 1. Cosine over sine would be cotangent, and they're both squared, so it would be cotangent squared. The reciprocal of sine is cosecant, so this would be cosecant squared. And you see how we used the Pythagorean identity and also a quotient identity and a reciprocal identity all together form this new identity. But it's the same one that we started with, it's just written differently. And let's do it again. Let's start with sine squared plus cosine squared equals 1. And this time let's divide through by cosine squared. So if we do that, then when we simplify, sine over cosine is tangent, so this will be tangent squared. Cosine over cosine is 1. And 1 over cosine is secant, so this will be secant squared. And there's the third form of our Pythagorean identities. Now in example 6 it says, find the sine of theta and the tangent of theta, given that the cosine of theta is negative square root of 3 over 4, and the sine of theta is greater than 0, or in other words, the sine of theta is positive. And we are going to use our identities to do this, but then I'm going to show you an easier way than using the identities. So I want you to just hang in there with me. I want you to see how the identities work, but then I want to show you an easier way using the Pythagorean theorem instead of the Pythagorean identities. So first, let's pull out the identity and look at it. Sine squared plus cosine squared equals 1. And now this identity relates cosine to sine because we are looking for sine and we know cosine. So I'm going to plug in the cosine value here and use that to find the sine. So I replaced cosine squared theta with the value of cosine squared. And so now let's work this out. Negative square root of 3 squared would be positive 3. And on the bottom, 4 squared would be 16. And that equals 1. So sine squared theta plus 3 over 16 equals 1. Now subtract 3 over 16 from both sides. We know that 1 is equal to 16 over 16. So 16 minus 3 is 13. That is 13 sixteenths. Sine squared equals 13 sixteenths. Now do the square root of both sides. Normally doing the square root of both sides would require us to put in this plus or minus, but they told us in the problem that sine was positive. So I'm going to go ahead and choose the positive sign and throw out the negative. And I also have split up this one radical so that the top has its own radical and the bottom has its own radical. If you don't remember that from algebra, that was the quotient rule for radicals, and we always do that so that we can rationalize the denominator. In this case, the square root of 16 is 4, which is already rational. And so the sine of theta is square root of 13 over 4. Now to find sine, or rather to find tangent, I already know sine and I already know cosine. So let's use our quotient identity. Tangent equals sine over cosine, and sine is this fraction and cosine is this fraction. So I've simply plugged them in here. Now they're pretty ugly right now because it's a fraction made out of fractions, but if I multiply the top and the bottom by 4, which I'm allowed to do because I'm doing the same thing to the top and to the bottom, those 4's will simplify away. I hope you learned in algebra how to simplify complex fractions. And that leaves us with square root of 13 over negative square root of 3. Now we know we're not ever supposed to leave a negative in the bottom, and we also know that we should rationalize our denominators. So I'm going to multiply by square root of 3 over itself. That will leave us square root of 39 in the top, 3 in the bottom, and I moved that negative sign from the bottom to the top. Now I want to show you an easier way to do example 6 using the Pythagorean theorem and the trig function definitions rather than the Pythagorean identities. So I hope that this is the way that you will use most of the time because it's faster. So it says find sine of theta and tangent of theta, given that cosine of theta is negative square root of 3 over 4, and sine of theta is positive, just like the last one. So I'm going to start by figuring out what quadrant theta has to be in. Now they tell us that sine is positive, and they also give us a cosine that's negative. So quadrant 1 is out because cosine's positive there, and I think we're going to have to choose quadrant 2 because sine is positive there but cosine is negative. And let's just draw an angle where this would be theta here. But we're going to draw a little invisible line here down to the horizontal axis, and using the definition of cosine we know that this is horizontal over hypotenuse. So the square root of 3 over 4 is the horizontal side and the hypotenuse side. We'll just label our triangle square root of 3 over 4. And now we're supposed to find the unknown vertical side. So the Pythagorean theorem will help us do that. We're looking for a leg, so we'll be subtracting the squares. So 4 squared minus square root of 3 squared gives us 16 minus 3, which is 13. So y squared is 13. That means y is square root of 13. Now that we know all 3 sides of the triangle, we can find any function we like. So sine is vertical over hypotenuse, which would be square root of 13 over 4, and it's positive because we're in the second quadrant. And tangent is negative vertical over horizontal, so it's negative square root of 13 over 3, or square root of 3 rather, and then we have to rationalize it. So it comes out negative square root of 39 over 3. And that's exactly what we found before, but I think, it's just less algebra, it's just more familiar to us. So this is usually the fastest way to get the job done, and you don't have to use the identities to do the problems in the identities section of this part of the textbook. I want to do one more that's similar. This one says find sine of theta and cosine theta, given that tangent of theta is 4/3 and theta is in quadrant 3. So the first thing I'm going to do is draw a sketch of theta in quadrant 3, and here's my little line going to the horizontal axis. So I think of the definition of tangent as vertical over horizontal, and I label my 2 sides, the vertical and the horizontal, with 4 and 3. And now I have to find the hypotenuse, so I'll add the 2 squares together. And I know that 4 squared plus 3 squared is 16 plus 9, which is 25. So r squared is 25, that means r is 5. And now I can find any functions that I like. So sine would be vertical over hypotenuse, and we're in the third quadrant where sine should be negative. So it'll be negative 4 over 5. And then cosine would be horizontal over hypotenuse, and again we're in the third quadrant where cosine is negative. So negative horizontal over hypotenuse, negative 3 over 5. And now I've picked out just a few from the end of the section. Page 37, numbers 85, 87, 90, and 91. Suppose that theta is between 90 and 180. Find the sine of each function value. So we know now that the sines of the functions depend on the location of the angle. And for each of these angles, we're going to use the location of theta to find the location of the given angle, and then we'll use ASTC to determine the sine of the function. So for the first one, I know from the instructions that theta is between 90 and 180, but I need to find where 2 theta is. So if I multiply this by 2, I'll have to multiply these other values by 2, and that tells me that 2 theta is between 180 and 360. Now that covers 2 quadrants, but in both of those quadrants, it would be quadrant 3 and quadrant 4. In both of those quadrants, sine is negative, so I know that the sine of 2 theta is going to be negative. If I do the same thing for number 87, I still start with theta's between 90 and 180, but now I want theta over 2, so I'll divide this by 2. That means I divide the other values by 2. And theta over 2 then is between 45 and 90. Well, that's quadrant 1. And in quadrant 1, tangent is positive. For number 90, I take the same inequality, 90 is less than theta, which is less than 180, but I need to know now not theta, but theta plus 180. So if I add 180 to that, I add 180 to every piece, that gives me theta plus 180 is between 270 and 360. Well, that's quadrant 4. And in quadrant 4, tangent should be negative. And then for cosine of negative theta, still start with the same inequality, but I don't need theta, I need negative theta. So if I put a negative here, I'll have to put a negative everywhere. But remember that when you multiply an inequality by a negative, it flips the inequality over. So negative theta is between negative 180 and negative 90, which is here. You know, if this is 0, this is negative 90, this is negative 180. So negative theta would be here, and this is the third quadrant, and in the third quadrant, cosine is negative.